Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Computer science departments across the country are beginning to develop courses that cover this underlying theory. And the things that you begin to see in these courses are sections on random graphs, phase transitions, giant components, spectral analysis, small world phenomena, and growing graphs. This tends to be what the kinds of things that they are covering. And I will talk a little bit about these so you'll know what these topics mean. So when I took graph theory back in the 50s, graph theory had to do with small graphs that you could draw on a piece of paper, and whether a theorem was true or not for a given graph depended on precisely which edges were present. And a typical theorem was a graph is planar if it does not contain a Kuratowski subgraph as a contraction. So as long as one of these two subgraphs were not present, it was planar. Well, but if you had a planar graph and added a single edge, all of a sudden it might become non-planar. And the reason that that's not of interest, theorems like that are not so interesting today, is we're interested in large graphs with billions of vertices, and the exact edges that are present are not critical. If I take a graph and erase 1,000 edges, and this changes some property of the graph, that property was probably not an interesting property. And so we want to know what are the theorems that are invariant under reasonable changes of the graph. And the theoretical basis, maybe it's going to be a theory of graph generation, and whatever it is, we want it to be invariant to small changes in the definition. And also we need to be able to prove some basic theorems. So one of the first models then for a random graph was that due to Erdős and Rényi. And their model is they started with n vertices, and each of the n squared potential edges is present with independent probability, some probability p. And if that's true, and you calculate the degree distribution, what you will do is you will get a binomial degree distribution that looks something like this. Okay? And so that's a nice theorem about this random graph. But the difficulty with this particular model is if you look at a real graph. And I just picked, I think this is United Airlines route map. And here, cities are vertices, and edges correspond if there's a scheduled flight between two cities. And now if you look at the degree distribution of this graph, you'll notice it is anything but binomial. Chicago has very high degree. I guess that's Denver, high degree. But then there are some cities, many large number of cities, very, very low degree. And so somehow the Erdős-Rényi theory of random graphs does not capture what's happening in this route graph. And in fact, I just didn't pick a bad graph. If you pick any real-world graph, you will discover it does not fit the Erdős-Rényi model. So what are we going to do? Well, one approach to that is we've looked at generative models for graphs. And what people do is they start out with a small number of vertices, and at every unit of time they add some additional vertices and some edges and let the graph grow. And if you do that, then you have to have a rule for where you're going to place the edges. One possibility is you might say, well, we'll just pick two vertices with uniform probability. That would be one possible model. Another one is preferential attachment. I'm going to let the probability that I will pick a vertex for the endpoint of an edge depend on the degree of that vertex. In other words, as you start to build up edges, it's more likely that you will get additional edges. And if you pick that particular model, you do indeed get a power law degree distribution which matches what you find out in real-world graphs if you look at the internet or things like that. Okay. Now, one of the points I wanted to make is that it doesn't matter where you get your graphs from. they're going to have the properties that I'm talking about. So I went into Science magazine and looked around for something I could convert into a graph. And I found a database that had 2,730 proteins. And they defined interactions between proteins, and there were 3,602 interactions. So I created a graph. The vertices were proteins. The edges were pairs of proteins that interacted. And then what I did is I wrote a little program to find all the connected components in this graph. And here I've plotted size of component, and underneath the number of components of that size. So that there were 48 proteins which didn't interact with any other protein. There were 179 pairs of proteins which just interacted with one another. And then there were 50 triples of proteins where the 3 proteins interacted, and so on. And you see by the time you get up here to 11 proteins, there was only one set of 11 proteins that interacted. Then there was one of 16. And then I wondered where the other vertices, the other proteins were. And if you look way out here, there is this component out here with 1,851 proteins which interact in a connected component. And needless to say, people have called this a giant component. And it isn't that it's just that I was lucky that I picked this particular database that I found this giant component. If you go out and basically pick any database you want, you're going to find this particular behavior. So there's something fundamental about it, and we should understand it. And so I'm going to just show you how it comes about. If you go back to what was the GNP model, I put down n vertices, all isolated vertices initially, and then I start putting in edges uniformly at random. And then what I'll do is I'll compute the number of connected components at each unit of time as I go along and see what happens. So initially I have 1,000, I started with 1,000 vertices. I'll have 1,000 components, each isolated component. I put in the first edge, then the number of isolated vertices drops to 998, and there's a pair of vertices connected by an edge. After I've put in a few edges, I get this distribution of components like this. And when I get a few more, all of a sudden you start seeing some large components forming and moving out. And then finally, when you get about 1,000 edges in, it turns out this giant component forms with 514 of the vertices. And you have the same kind of structure that you had in that database that I got from Science. And so understanding these giant components and how this phase transition takes place where this forms is interesting. It turns out this phase transition has 2 phases to it. There are 2 jumps take place in the formation of that. And I borrowed a slide just to show you that this giant component exists in the World Wide Web. This was a slide created at IBM Almaden, but this was back when the World Wide Web only had 200 million web pages. But at that time, and by the way, the World Wide Web, here it's a directed graph rather than an undirected graph. And so we're looking for a strongly connected component, looking at where you can get from vertex A to B, and then there's a path from B back to A. And indeed, there was a strongly connected component that had a quarter of the vertices, 56 million of them. 44 million of the vertices you could reach the strongly connected component from, but couldn't get back. And there are 44 million you could get to from the strongly connected component, but couldn't get back. And then there are other little pieces and some disconnected components. And the structure of this graph fits the mathematics of random graphs very precisely. So there's some other things that I want to talk about. So I'll just mention certain technologies, certain ideas in case people aren't familiar with it. One way is if you have a document which is in digital form, you can take all of the words in that document and sort them and count how many times aardvark occurs, abacus occurs, antitrust occurs, CEO occurs, and so forth. And you can form a vector. And you can represent this document just as a vector of the number of occurrences of words. And it turns out this vector is sufficient to pretty much tell you what this document is about. And I don't think anybody here will have any trouble guessing what this document is, the content of it. So I'm going to tell you about a search that I did. This is a number of years back. I wanted to find a result on Boolean circuit theory. And not thinking, I just typed the word gates into my search. And of course, what I came back with, I used a search engine which at that time clustered the papers that it gave you back. I got 500,000 hits on Bill Gates, 177,000 on Gates County. I didn't even know there was a Gates County. Baby gates, gates of heaven, automatic gates, fence gates, and finally 19,000 papers on Boolean gates. Now, if you had ordered these web pages back by some sort of ordering, you can imagine how far down that list I would have had to have gone until I got the first paper on Boolean gates. So what I would like back instead of this list is I would like the search engine to cluster them for me. Because if it had clustered them for me, I could have said, gee, I don't want those. I want Boolean gates, and I would be right into my 19,000 that I wanted. If you had wanted something on Bill Gates, well, it would have clustered them, and you would have had a bunch of subclusters, Microsoft, Windows, antitrust, and so forth, and you could go down a couple levels to get what you actually wanted. So one of the questions is how do we do this? But something that is more important, and here there's an interesting research topic, if I wanted to cluster books, one way I might do it is I might cluster them as mathematics, physics, chemistry, astronomy. I might cluster them by content. But alternatively, you might want to cluster them as children's books, textbooks, reference books, general population. And how do I go about determining which clustering I want? Presumably, you're going to change your distance measure between papers depending on how you want to cluster them. And how do you go about doing that? And one of the first things you want to know is, suppose I cluster this data set and I get a clustering. How do I know that I haven't just found some random clustering as opposed to some clustering that has some real structure or meaning? And how do I know, as I'm searching the space of all distance functions, how do I know when I'm moving towards a distance function which is going to give me a reasonable clustering? These are the kinds of questions that we would like the mathematics to be able to answer for us. Okay, so what's the theory needed to support this future? We're going to have to learn how to deal with large amounts of data. It's going to be noisy data, and there's going to be lots of outliers. It's going to be high dimensional, and it's quite possibly going to be power law distributed. Because you saw in that first graph that we put up, the United Airlines route graph, that the degree distribution is power law distributed. And it turns out this is going to be important. You'll see in a minute. So what I'm going to do now is I'm now going to switch. That was the sales pitch for the area. Now I'm going to switch and talk a little bit about the mathematics. But I picked subjects which I think everybody will understand. And one of the first things that we need to understand is something about high dimensions. And so I'm going to talk a little bit about how at least my intuition, which was formed in 2 and 3 dimensions, was just simply wrong when I started thinking in high dimension. So the first example I'm going to give you is that of a unit cube. So this cube is 1 unit in each direction. And no matter what dimension I draw that unit cube in, its volume is going to be 1 cubic unit of that dimension. Okay? But what would have happened if I had taken a unit sphere, a sphere with radius 1, and started to increase the dimension? Well, when it's in 2 dimensions, you have a circle, and the area is pi r squared, so the area would have been 3.14. When you go to 3 dimensions, I think it's 4/3 pi, so it's a little bit bigger. And in fact, as you increase the dimension up to about 11, the volume grows. But when you get beyond 11, the volume starts to shrink. And in fact, the volume of a unit sphere goes to 0 as the dimension goes to infinity. Now, it turns out, if you think about it for a while, it's obvious. But that would not have been the answer that I would have given you if you had asked me what is the volume of a 1,000-dimensional unit sphere. Okay, so let me show you why that happens. And I'm going to do a series of drawings here. Unfortunately, your PowerPoint only allows 2- and 3-dimensional drawings. So I'm going to do them all in 2 dimensions, but I'm going to raise the dimension. So they won't be quite right. But here's a unit sphere. So the distance from the center out to here is 1 unit. And then I drew a unit square. So the coordinate here is, well, the coordinate here is 1/2 and 1/2. Okay? And you see that the square is completely inside the sphere. Okay? Because this radius here is 1/2 squared plus 1/2 squared takes square root. Well, this is 1/4 plus 1/4 is 1/2, so it's the square root of 1/2. And so this point is clearly inside. If I go to 4 dimensions, though, look what has happened. This distance here is now 1/2 squared plus 1/2 squared plus 1/2 squared plus 1/2 squared. These are each 1/4, and there's 4 of them. They add up to 1. This vertex has moved out to the surface of the sphere. And in fact, if I go to d dimensions, what's happened? Well, this distance out to this vertex is now square root d over 2. So if d were 10,000 dimensions, this is 50 units out, and this radius of the circle is only 1. So this vertex is way outside the sphere. But this point right here is still inside the sphere. Okay, so maybe I should have drawn this in d dimensions to look something like this. That the sphere is down here, and this cube, most of the volume of the cube is out in these places, and this sphere is indeed, its volume is going to 0, even though there are little bits of the sphere outside the rectangle. Okay. So let me point out something else about high dimensions. If in 2 dimensions I put a number of points down at random, and I ask what is the ratio of distance between the 2 points which are farthest apart and the 2 points that are closest, I'm going to get a fairly big number. Okay? This distance looks like maybe 5 times this distance. But what would happen if I put these points down in high dimension? It turns out that the distance between every pair of points is going to be the same. Why is that? Well, the reason for that is if I put n points down at random in d dimensions, where d is high, and I calculate the distance between 2 points, x and y, well, the distance squared, I take each coordinate, I square it, and sum them up. Now, the difference between x and y is some random variable. It has a mean and a variance. And when you add enough of them up, the distribution of this sum is, by the central limit theorem, is going to become Gaussian. And it'll have an expected value, which is the expected value of this variable squared times the number. And it will have a variance, which is fairly small. And the points will be, these values will all be tightly concentrated around some expected value. So if you're looking at points put down in random in high dimension, and you're calculating distance between them, it's going to be a very unstable calculation. Okay. So let me tell you something about Gaussian distributions. So I drew a Gaussian here. And if we look at the Gaussian in 2 dimensions, and we ask, and I'm thinking of this as a probability distribution, and I ask, where is the probability concentrated? Well, if I go out, let's say I went out 3 standard deviations, all the probability mass would essentially be in this region here. Okay, it would all be around the origin, and you'd have a nice distribution there. But what happens in high dimension? Turns out in high dimension, the picture is not like this at all. If you're in high dimension and you generate points according to a Gaussian distribution at random, there won't be any points close to the origin. They will all be out in an annulus, a very narrow annulus, whose radius is square root d. Okay? Now, why did that happen? Well, the reason for that is if you take a little annulus close to the origin, say a sphere close to the origin in high dimension, that sphere has volume 0. So even though the probability distribution is high there, when you integrate over 0 volume, you get 0. As you move out from the origin, these rings contain more and more volume, so the integral has a chance of being bigger. But when you get too far out, the probability distribution drops off, so the probability goes to 0. But there is this narrow ring in here where all of the points will lie. Okay? So that says, what if I have two processes which are generating points at random in high-dimensional space, and I'm going to give you these points. These are data points. And I want you to separate them into two piles, one generated by one process, one generated by the other process. How do you go about doing it? Because all the points from one process are going to be in this ring, points from the other process are going to be in this ring, and these two rings overlap. I mean, if the rings are far apart, then you have no problem separating them, okay? But I'm talking about data, which is going to be hard to separate. Well, one thing you should notice is that the intersection of these two rings is sort of like a lower dimensional surface, and its volume is going to be very small, so there isn't going to be much in that little region or that little region. So we have a hope. Okay. So this is in dimension 500. I generated two sets of points, 1,000 each. Some of them are blue and some of them are green, and you can see, I couldn't draw this for you in high dimension, but I projected it down onto a random two-dimensional space. And you can see that these points highly overlap. And now the question that I'm going to ask you, if I hadn't colored the points, if I had had them all black, could you tell me which of those points came from one Gaussian and which came from the other? Well, it turns out it's easy to do. And let's just go through a little math. So the distance between, if I take two random points from the same Gaussian, let's see how far apart they would be. Well, first of all, the points are going to be in a thin annulus of radius square root d, that from the earlier slide. And I'm going to approximate that by a sphere of radius square root d. And I'm going to claim if you put 2 points at random on a sphere, they will be square root 2d apart. And the way to see that is when you put the first point down at random, why don't we adjust our coordinate system so that that point is at the North Pole? Okay? That's the first random point. When I put the second random point down, where is it going to be? Well, I claim it's going to be in a very narrow band around the equator. And why is that? Well, the answer is this is a sphere in high dimension. All of the surface area is in this little band. And the surface area out here is essentially 0. So the point is going to end up here, round in here. Okay? And this is one of these places where our intuition in low dimension may not be right. But if you think about this for a little bit, you'll see that this is true. And if this is true, then essentially these two lines are almost orthogonal. And if they're each of square root d, then the distance from there to there is 2 square root d. So now let's say I take 2 points, one on one Gaussian and one on another Gaussian, where these Gaussians are separated by a distance of delta. Then what is the distance from this point to this point? Well, what I'll do is I'll break that distance down into two components. I will map this component over here to this other Gaussian, and this distance going across here is delta, and this distance, since these are two random points now on this Gaussian, is square root 2d. And so when I take delta squared plus square root of 2d squared, square root, this is the distance between this point and this point. And these distances are highly concentrated. The distance is very unlikely to differ from this by very much. Now, if it turned out that the difference in distance between 2 points on different Gaussians was bigger than the distance between 2 points on one Gaussian, then the following algorithm would work. I'll calculate all n squared distances, and then I will cluster things and put all of those which are close together in one cluster, close together in another cluster, and I'll be able to do that as long as this distance is greater than this plus some constant, which is going to depend on the size of that annulus. Okay, so if I take this and take the square root, and this is something I haven't quite figured out yet. If you're wondering what this L is here, this is just my not quite understanding how the equation editor works, interacts with PowerPoint. This is ... And sometimes it's ... and sometimes it's not. Okay, so forgive me, I'll figure it out someday. But if I take this, do the binomial expansion, you'll notice there's a 2 square root d here and a 2 square root d, so I can subtract it off. And if I take this second term and compare it to this, I need this quantity to be greater than this, or I need the distance delta to be greater than d to the 1/4 power. So if those Gaussians are separated, so in 10,000 dimensions, if they're separated by 10 units, I can tell you which Gaussian a point came from. Okay. Now, actually, you can do much better than this. This is some early work. And by the way, I'm not talking about my own work. This is work of many researchers across the country that I better say that. Okay. So one of the things, a general technique, is that you want to reduce the dimension of the space you're working in. And you'll see why in just a minute. So if I could project the points onto the subspace that contained the centers of the Gaussians, then I'd be working in a much lower dimensional space. And let's say there were k Gaussians, not 2. So if I could find the k centers, and I could put a plane, a k-dimensional plane through them, and then project onto that plane, all of the points, the component of a point which is off that plane is simply noise. And what I'm doing is I'm throwing away the noise. And I'm then working in a lower dimensional space which captures all of the signal. So what happens, this is the plane through the centers. And the centers, since the centers are on this plane, when I do a projection, the distance between the centers doesn't change. But the distance between points, when I project the points on here, gets reduced by square root d over k. And so then, instead of having a d here, which was the dimension, which is a number like 10,000, you have a number k, which may be 3 or 4 Gaussians you're trying to separate. And now all of a sudden, the distance delta, all it has to be is greater than some constant involving the number of Gaussians you're working with and the size of that annulus, which depends on the variance of the Gaussians. Okay? So projecting onto the space through the centers gets rid of the noise and lets you separate things much more generally. Okay. Now, okay, I'm going to take a little break on that. I'm going to come back to that because I want to talk about it. I talked about Gaussians. And some of you are probably saying, what's he doing with Gaussians? Doesn't he know real data isn't like Gaussians at all? And so we will come back and we'll tell you how you have to modify that if you're not using Gaussians, because it's fundamentally different. But I want to now talk about some work on spectral analysis, because the question is how do I find the centers of those Gaussians in order to find the plane to project onto? And you do that by a spectral decomposition. And here's some work in physics helps you. It turns out if you look at the eigenvalues of a random matrix, a physicist by the name of Wigner, about 1900, showed that they're distributed in a semicircle and what the bounds of them are. And if the eigenvalues are within certain range, you know they're due to random noise. If they're outside that, they're due to structure, and that tells you how many things you're looking for, and that tells you how many eigenvalues to zero out and how to find the plane. Okay, so now I'm going to talk about some work that was actually done here. It was done in Microsoft. It may have been done in California. I'm not sure if it was done here. By Frank McSherry, who is probably one of the world's experts on spectral analysis. And he has the following model. You have a matrix where you have certain probabilities. And I took a simple block-structured matrix where the upper left-hand corner, the probabilities are all a half. Here, the probabilities are all a quarter, a half. So think of this as a matrix, a 10,000 by 10,000 matrix. Okay? And what he's going to do is he's going to take this matrix of probabilities and randomly round them into a 0-1 matrix. So then I'm going to have a 0-1 matrix, and what I would like to do is from that 0-1 matrix recover this structure. Okay? So it's very similar to the Gaussians that I was trying to separate, I don't tell you for a given element here whereabouts in this matrix it came from. That's what I want you to tell me. Okay. So what he did is he did an eigenvalue decomposition. So these are the left singular vectors, the right singular, the eigenvalues. And what he did is he would discover that 2 of these eigenvalues were fairly big. The rest were all in the random noise. So he would zero these out and then multiply this back together. And what that would do is that would give him a rank 2 matrix. And from that rank 2 matrix, he can prove rigorously that he can recover the block structure that you originally started from. And this was a really nice result. It's by the way, it's much harder. I'm putting it up here. It's kind of trivial. It's not this simple at all. There's some really deep mathematics to do this. And I'll come back if I have time and talk about a piece of it. But Papadimitriou and Mihaly then made a statement at a conference. And they said, hey, wait a minute. Most data is power law distributed. And so your model, you should have started with the structure along with the degree distribution you want in the graph. Multiply this together to get your matrix of probabilities, and then randomly round to 0, 1. And then if you add up a row and look at the sums of the rows, those numbers will be power law distributed. Whereas in McSherry's model, they all added up to a constant. Okay? Well, what Papadimitriou and Mihaly said, if the degrees of a random matrix are power law distributed, then the major eigenvectors are associated with the neighborhoods of the high degree vertices rather than the structure of the graph, and your work doesn't work. Well, for a little while, people were a little bit disturbed because all of a sudden spectral analysis went out the window. But the following observation can be made. You can think of this matrix as part of it being signal and part of it being noise. And what you want to do is you want to increase the signal to noise level. Okay? One way to increase the signal is to multiply every element of the matrix by some fixed constant. The difficulty with that is if you multiply every element of the matrix by a fixed constant, you've increased the noise also. Okay? However, the bounds on spectral analysis are determined by the maximum noise of an element, not the average. And so what we did is we multiplied all the low variance elements by a constant to increase the signal without increasing the maximum noise, and then we're able to prove that you could recover the matrix. And just to show you how to do that, the variance of a random variable, if you have a variable which is 0, 1, 1 with probability p and 0 with probability 1 minus p, its variance is approximately equal to p if p is small. Now, there are 2 ways of modifying x. One of them is you can multiply the probability by a constant, and I guess I missed a c here, this should be 1 minus cp, and change the probability of when the variable is a 1 and a 0. The other way you could modify it is you could change the value of the variable, but not change the probability. Okay. In the model, when you're making it power law distributed, you're changing the probabilities. But when you're trying to recover it, you don't get to touch the probabilities. You don't have access to them. You only have access to the variable. And notice that when you change the probabilities, you change the variance by a constant. When you change the value of the variable, you change the variance by the square. So what you want to do to undo the effect of putting a c here is multiply the value of the variable by square root c down here. And if you do that, it turns out that you will correct things, and indeed, McSherry's work is valid, and it does work for power law distributed graphs. So that was good. Now, one of the things I want to just mention is power law distributions arise in many different contexts. And in the slide that I just talked about, I talked about data and how you correct for the power law distribution in data. But if you're doing queries on the web, your queries also have a distribution. And if your search engine is just going to be a generic search engine, you're not going to look at you're going to look at the general distribution of queries and optimize your search engine for that distribution. But notice that if you have a single individual and you know the queries that that individual makes, you can optimize your search engine for the particular distribution of queries that an individual makes, and you can get answers which will be better for that individual than you will. So this mathematics is, although I'm giving it in narrow little problems, it applies much more generally than I'm alluding to. Okay. So now what I want to do is, and by the way, there are just many, many researchers around the world who are doing things similar to McSherry. And there's a general theme in all of their work. And so what I want to do is I want to try to extract out that general theme and talk a little bit about it. So what they do is they use singular value decomposition to find a reduced subspace. They project their data onto the reduced subspace. They cluster. And then, although the SVD minimizes the sum of the squared error between points in their expected values, so you can't do any better in terms of the average error, it turns out that the error is not uniformly distributed. And because it's not uniformly distributed, there are some outliers, and those outliers get misclassified. And so a very significant piece of what McSherry did was how to clean up afterwards and reclassify the outliers to get them into the right category. So he reprojected the data onto, well, what he did is he took the clusters, he found the cluster centers, put a space through the cluster centers, and then reprojected the data onto that space, reclustered, and then was able to prove with high probability everybody was correctly clustered. And this is a general theme. I don't have time to go into other people's work. In each case, the details are different, but this is roughly the outline of how it goes. Okay. Now, what I'd like to do is go back and show you a problem when you don't have Gaussian data and how to fix it. So let's say I have two Gaussians. One of them is at 0, 0, dot, 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 0, and the other is centered at 1, 0, dot, 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 0. So here it is. One's here, and on one coordinate, the other one is centered there. And the distance between these two centers is 1. And I'm going to take another situation where one of the Gaussians is at the origin, and the other Gaussian is at the point 1, 1, 1, 1 multiplied by 1 over square root d, so that the distance between here and here is the same as the distance between here and here. It's just that in this case, you're off in all coordinates a little bit, whereas here you just shifted along one coordinate axis. Okay. Now, if you have spherical Gaussians, you're going to say, what difference does it make? If you're down in this situation, just rotate your coordinate axes, and you're up here, and indeed you're right, it doesn't make any difference. But the trouble is you don't have Gaussian distributions. And now I'm going to go through something where I hope I can get this across. If not, talk to me afterwards. I'm going to consider binomial distributions. And so for binomial distributions, I've got a variable. Each coordinate is going to take on a value 0 or 1. And so you think of a hypercube in high dimension, and I'm picking a vertex. And I'm going to pick vertices with equal probability at random. And I'm going to have two hypercubes, and I'm going to pick vertices. But I'm not going to paint them blue and green. I'm going to paint them all black, and I'm going to ask you, which hypercube do these belong on? Okay? And now I'm going to show you that the two situations are fundamentally different. So here's one hypercube, and then I shifted it over and drew another one, but I shifted it in just one dimension. Okay. If I now project the vertices of these two hypercubes down, all the vertices over here, which is half of them, will end up here. Half of the vertices from each of the hypercubes will end up here, and the other half here will end up here. Okay? And if I ask you to separate, I just give you these vertices and ask you which hypercube did they come from, what are you going to do with these? You're going to guess, and half of your guesses are going to be wrong. So there's nothing you can do. Okay? However, if I had moved the hypercube up this way, and I move it the same distance, but I just move it a tiny bit in each dimension, okay? And then I draw this line through here, and I project the vertices down. What happens? Well, all the vertices from the solid hypercube will be in a Gaussian here. They'll be concentrated about their expected value. And all of those from this other one will be here, and they'll be concentrated about their expected value. And you see you can easily sort out which one did they come from. Okay? And so what you want to make sure is that when you do a projection, that the things you're projecting end up concentrated about their expected value. And that's what was wrong back here. These didn't end up concentrated about their expected value. The expected value is in the middle here, and you would have liked them all to end up there. Okay? Now, I'm not sure that this picture, did this picture come across? Okay, because you might say, well, what happened to the vertex here? Well, there is one vertex there. And when you move in a little bit, there are d vertices here, and then there are d squared. But that's negligible to those in here, because in here there are 2 to the d over d vertices. And that's why they're all essentially there. So this suggests that we define a concept of balance of a unit vector. And that is how uniformly the coordinates contribute to its length. Okay, and so the definition of balance is the maximum coordinate divided by the length of the thing. If it's a unit vector, it's just the maximum coordinate. Okay, so the general method is you want to project data onto the singular value subspace. You want to cluster. But now, what you want to do is you want to make sure that when you reproject, that somehow you get your data to be concentrated about its expected value. And how do we go about doing that? Well, when I cluster and I calculate the centers, if I had the centers, oh, by the way, if I'm going to be able to tell you which hypercube the points came from, the centers are going to have to be balanced to start with. If they're not, there's nothing you can do about it. But we will assume that they are. How do I know when I take these clusters and calculate their centers and put that space through, that indeed when I project onto that I'll be projecting onto something which is balanced? Because we won't have the true centers, we will have approximation to the centers. And so we don't have that balance. So what we do instead is we draw lines through all k-squared pairs of cluster centers. Now, these lines may not be balanced, but we know close to each of these lines there is a balanced line. And so you write a little algorithm which will take a line and perturb it slightly to make it balanced, but not perturb it so much that you'll introduce too much error. Okay? And that's what we call smoothing the lines. And then we're going to project onto each line and cluster. And so let's say I have 3 lines, and I have the 3 centers, A, B, and C, and I have this point out here. I'll project it onto each line. Now, you might say, gee, this point projects here very close to A. But I'm not going to put it in cluster A, because this point, whatever cluster it belongs to, every line through that point, this will end up closer to that point than the other point the line goes through. And so I run a simple algorithm. I take each point, and I look at each line, and I look to find a center such that all the n-1 lines through that center, this point ends up closest to this. And then that will tell you where to put that point. And it turns out this is a general theme that works. Okay. So what I'll do, I'm going to run out of time if I go into too much more. So let me just kind of suggest, I think what I've done is I've shown you how there is some mathematical theory underlying some of the things that we're doing and suggested that it is important. And then I'd like to show you some problems that what we would like to do is we would like to develop the theory that handles these. So when a customer makes a purchase, what is he likely to buy? And obviously this is going to be an important question, economic question, and we would like to be able to make that prediction. And there is theoretical work underlying this telling you how to make good predictions, and that theory is important. How can we extract information from a customer's visit to a website? What web pages were visited, what order, how long did they stay on, and how can we produce mathematics which will tell us what we can about the customer from that. So the collaborative filtering, I talked just a little bit about it. We'd also like to detect changes over time. It would be nice to know if there's changes in a market or changes in a buying habit before it became obvious to everybody. And we'd like to be able to extract information from large data sources, detecting changes in patterns, and I may be able to tell you a little bit about that. We want to detect these changes before they become obvious. And if you detect a change, how do you know whether it's a random fluctuation or it's a real change? And you ought to do something about it. These are things that we would like theorems that would give us some mathematical idea on. Okay. How large must a change be in order to distinguish it from random fluctuations? What I'd like to do is I'd like to tell you about an experiment that we did with, and this is 200 graduates did it. I shouldn't say we. They did all the work. On the seer database. Now, the seer database is a collection of papers, computer science research papers. They wrote, I forget the names of the people at NEC, who wrote a little crawler that went out in the web and looked at web pages and asked, is this a research paper? If it's a research paper, is it a subject matter of computer science? And if so, they pulled it back into the database. And then they extracted the title, the author, and the citations at the end of it. Okay, so it was a database that had 300,000 documents in it. And for each document, they had pointers to all the documents that they referenced. And there were 7 million references to 2 million distinct documents. Many of the documents they referenced weren't in the database. Okay? So what we wanted to do is, using this link information, is cluster this database. And what we wanted to do, since the papers had a date on them when they were written, is cluster it over a couple periods of time and see if we could detect changes in what people were publishing in. Okay. This data has a very low signal-to-noise ratio, and so you have to find a way to strengthen the signal. And I'm going to skip over much of what we've done because I see I'm running out of time, but let me just go through here to tell you how we tried to improve the signal. What we did is we used an agglomerative clustering method. And agglomerative clustering is very unstable. We went into the database and we erased one reference. We took one reference in one paper and erased it, and then reclustered. And it turned out the clusters were just fundamentally different. And with that, you said, my gosh, I'm not going to believe anything if it's that unstable. But we then did the following experiment. We randomly selected 95% of the papers and clustered them. And we did that 100 times. And in each clustering, we took each cluster and we found its best match in another clustering. And we looked to see if there were any clusters which appeared across all 100 clusterings. And it turned out, of the 300,000 clusters, most of them never appeared again. They were just random. But there were a few thousand clusters which appeared in every clustering. And so we called those stable clusters, and we assumed that those clusters had some significance. And you could imagine if you had a cluster, let's say, which is finite automata papers, the order in which those papers came together in that clustering is probably completely random because they're so close together. But you could clearly understand that before that cluster merged in with the cluster on context-free languages, the two clusters would form and then merge, okay? So that there would be places in this tree where there would be stable clusterings which appeared. And so what we did is we pulled out these natural communities, and indeed they corresponded to things that you could really recognize. Handwriting, speech recognition, audio, voice, wavelets, video images, mining, things like that. Okay. This is one community because this was supposed to be papers on computer science. And this community always showed up. And it looks to me like it's Greenland, not computer science. I don't know how it got in there. I think what happened is there was topic drift, which is another topic. How do you prevent topic drift? But anyway, what we did is we did clusterings for different time periods, and we were able to define emerging areas, stable areas, declining areas. And this is very similar to this work Sheparenko did in the earlier slide that I showed of the NIPS papers. And just to show you what the emerging communities were in 2003, roughly, when we did this. Digital watermarking, gene expression, support vector machines, semi-definite. And this roughly corresponds to my feeling of what was appearing in the literature at that time. So I'm just going to mention 2 more slides, and then I'll finish. I'll finish on time. What if you don't have Gaussian, or what if your distributions are something like Cauchy? And now a Cauchy distribution, what is interesting about it is it doesn't have a variance. The tails go off so fast that when you go to calculate the variance, the integral doesn't converge. And so the central limit theorem doesn't apply here. If you take a number of variables which are Cauchy and add them together, you don't converge on a Gaussian. But what turns out, you converge on a Cauchy. Cauchy plays the role that Gaussian does for a particular range of distributions. So what if you wanted to estimate the mean of a Cauchy distribution? Well, one thing you might be tempted to do is draw 100 random samples, average them together, and let that be the mean. Divide by 100 and call that the mean. Well, that doesn't help you, because if you take 100 samples and add them together and divide by 100, what's the distribution of that value? It's exactly the same as the distribution you started with. You just wasted your time. You should have just taken one sample. You would have done just as well. But what we need to do is we need to construct a theory that is going to allow us to handle distributions like Cauchy. And we're starting to do that. We start to understand how to do all the separations that we did before. We just don't know how to do it in polynomial time. But one of the things you might do...
So are you doing the stable distributions here rather than just Gaussian? You're doing all...
we would like to do, yes. We'd like to, but you have to do slightly different techniques. And this area, there's a lot of open things. We can't do this completely, although we just published a paper where we were able to show we could do some, but not in polynomial time. That's another catch.
There's some area where there are sort of different stable distributions.
Right.
Some which are nearer to the Gaussian, some are far from the Gaussian.
Right.
Do you see that sort of up to some point you can do things and then you can't?
No, we're in very preliminary stages here. Okay, and I have to be very careful what I say because I may get it wrong too. But we start to see papers in the literature now where people are able to do things with distributions which aren't, which don't have variances. And basically what they're doing is they're replacing spectral decomposition by, instead of using the 2 norm, which that is based on, they're using the 1 norm. So one of the things, if I wanted the mean here, what a statistician would do is say, well, why don't you just take the median? But then the trouble is what if the distribution is not symmetric? But one of the interesting research questions is what do you do with these distributions which are high there? So let me just conclude here. Let me just put a conclusion up. What I hoped I got across is that we're in an exciting time of change. Information technology is a big driver of that change. And the computer science of the last 30 years needs to be extended to cover the computer science of the next 30 years. And I think that this is a place where people can make very important contributions, and it will be great.